Oh, better. Well, today my light isn't on, so I'm going to assume that this is functional. Oops, excuse me. Okay. I have old assignments that I apparently never finished passing out after the exam, so not everybody. I got some people.
Oh, how do you write it? Oh, she emailed it? Yeah. All right, let me check my email. Thank you.
Mm-hmm.
See?
Thank you.
Amazing, man. Thanks.
Questions?
Okay. So I had that double take while I was prepping for class. I was like, where are all the homework assignments? Oh yeah, you guys didn't turn in homework last week. That's nice.
Oh, that's right.
Yeah, because it was post-exam. So, okay, let's open the lecture. Make sure we're on the right lecture for this week. Feel like I'm, there we go. Okay, we're in the right place. Lecture 6, so we're continuing our discussion about magnetism today. And I would have liked to have done lab first today, so you guys could work on your little race cars, but we are in the process of ordering the thicker magnetic wire. Richard ordered that Wednesday, and I haven't seen him yet today. So hopefully he'll let us know when it should be coming in. But I think it would be optimistic if it showed up today, unless they did 2-day shipping. So we'll go ahead with the lecture, and we can't really do experiment 1 until you've learned what we're learning today. So we'll, I think, inevitably have to do the lab after lecture today. So we'll do our clicker quiz questions from lecture 5. Here's the worksheet with the questions on them, so you can get your in-class participation points. And then we'll do a quick review of the magnetism concepts we learned last week. Yeah, Chris?
Can we just maybe touch briefly on the magnetic dipole moment? I'm not sure we covered that.
We didn't.
It was in the lecture material.
It was hidden from the, so if you actually open the PowerPoint, it was a hidden slide.
Oh.
Yeah, so we're not learning it. Yeah, it's,
Deleted.
yes. It doesn't come up a whole lot, and it's not critical to what you need to learn in here. So it's something I have taught in the past, but consistently.
So motion too?
What's that? Oh yeah, helical motion. I don't think we have that problem anymore. So it was like one problem, and so I just opted to not teach it since it only comes up very rarely. Yeah, thanks for asking. That can be confusing if you're not actually opened in PowerPoint. It will just print the hidden slides along with the rest of the slides if you have the paper copy. Yeah, so it might not be clear.
Sorry, last question. There was a homework problem that talked about DC motors in series. I'm not sure we talked about that in class, and if we did, I may have missed it. Is there
I don't think they mean motors in series. It's just called a DC series motor, which is what we learned. So there's nothing different than what we learned about motors. That's just what they're called. Any other questions before we get rolling? Okay. We're going to do a little bit of review and make sure you guys remember how to use your physics gang sign. A beam of electrons which have negative charge Q is coming straight towards you. So this little green dot is a beam of electrons coming out this way. You put a north pole of a magnet directly above the beam. The magnetic field from the magnet points straight down. Which way will the electron beam be deflected? Look around the room and see if anybody's actually using their right-hand rule. See a few people.
It's like doing this. Don't worry about it.
Okay. Anybody still need more time? All right, who thinks the answer is A? Who thinks the answer is B? Who thinks the answer is C? One vote. Who thinks the answer is D? 1, 2, 3, 4, 5, 6. Who thinks the answer is E? All right. So most people chose D, so why did you choose D? Those of you who chose D. All right, so explain what direction you pointed your fingers in order to come up with the answer that it would move to the right.
Well, I just used the right-hand rule and then used my index finger to point out from me, and then my middle finger to point down, and then that's going to my left. So then if I flip that around, because we're looking, it'd be like doing it in the mirror, then, well, not really, if the mirror reversed, but then I said it would be going to our right if it's the magnet's left.
Okay, so your index finger, you aligned with the direction of the electrons. And then you said your middle finger is down, so that's in the direction of the B field. And your right hand, or your thumb, then... What's that?
Yeah, it's an electron, so should it be to the left?
Oh, Vin was the only one that said to the left.
Oh my gosh.
Vin was the only one that was right. Oh! Okay, so the way Chris, and I'm not even thinking because I'm very tired today. So we get our right-hand rule right based on the picture, and then that added piece of information. It's an electron, so it's actually going in the opposite direction of what our thumb is doing. So that tricked me too. So Vin, you just knew that. You're like, yep, I got it all.
Sure.
Awesome. I'm going to assume that Vin did it all right. All right, any questions about that one? Should we check, see if the book is right? C was the answer. So, okay. When a charged particle moves through a magnetic field, the direction of the magnetic force on the particle at a certain point is what? Actually, Jordan, I think all of these are the same ones we did last week, so now you get the chance to be present for them. All right, who's ready to vote? You guys are all ready to vote? Okay, who thinks the answer is A, B, C, 1, 2, 3, 4, 5, 6, 7, 8, D, E? Okay, so those voting chose C. Is this sneeze ever going to come? Okay, so why did you guys choose C? Jan just remembered from last week. And what did you remember from last week? Just the magnetic force is going to be perpendicular to the magnetic field? Yeah, I all remember that. Okay, good. A particle with a positive charge moves in the xz plane as shown. The magnetic field is in the positive z direction. The magnetic force on the particle will be in what direction? Okay, is everyone ready to vote? Okay, who thinks the answer is A? B? 1, 2, 3. C? 1, 2, 3, 4, 5, 6. D? E. Okay, so 3 for B and 6 for D. No, 6 for C. 6 for C. All right, so we'll start with C. Why did the people choose C?
Has to be perpendicular.
Okay, it has to be perpendicular, but why positive and not negative?
Because it's a proton and an electron.
So explain to me with your right-hand rule in which direction your fingers went that got that result.
Actually, I think it's negative. I'm not sure.
Okay, Kevin's not sure. Someone else who chose C, want to give it a stab? Okay, moving on to the people who chose B. Anyone who chose B want to defend their answer? Yeah, Chris?
Well, alt effect. I looked at the picture rather than reading the question, and it appeared that B was kind of at an angle, but in the negative y direction, which then with the right-hand rule would have made it in the negative x direction. But then rereading the problem, it looks like it's in the xz plane, so they're both on the same plane. Is that
Yep.
what we're seeing? Okay.
Yeah, it's kind of, it's
Which then
coming.
in that case, it would be in the, I guess, negative y direction, so I will defend.
Okay. We have 2 people defending their answers who've defected in the process.
Yeah.
I didn't see that at all.
Yeah, I don't like the picture.
All right, well, maybe we should revote. Nobody voted for A before. Does anyone want to vote for A now? Nobody voted, or we had 3 people vote for B. Does anyone want to vote for B now? Is anybody still voting for C? 6 people, we have 2 left. Who's voting for D now? 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's quite a difference. Okay. Okay, so people who chose D, walk me through what direction my fingers are going to go to get to that answer. So my index finger is in the direction of what variable? V. V. So V is kind of like flat but at an angle. So do I keep it flat and at an angle? Okay. You guys all agree with that? Some people, yes. Anybody think it should be in a different direction? Okay. And then what about my middle finger? What variable is that associated with? B, yeah. Okay, and that's pointing out of the board? Okay, so, all right. So in order to do that, the physics gang sign, those are at 90-degree angles. So, but these are at 30-degree angles. So that, I guess, goes back to my first question. Because the way I've got it now, my B is coming out of the board, but my V is along the positive x-axis. Is that okay? Does that work? Or should I tilt it so that my index finger follows the direction of V and now my middle finger is off the B direction? Some people say tilt it. How many people think that my V should be directed along the positive x-axis so that B is along the positive z-axis? So you all think I should tilt it?
I have no idea.
I don't think it matters because y isn't involved, and so it's going to all be on the same plane. So no matter what we choose for the force, it's going to be perpendicular to them anyways.
Okay, so Liz says doesn't matter, which is true to get our answer. That part doesn't matter. So whether I do this or this, my thumb is still pointing straight down. So that gives us the answer that you guys chose. As to the point I'm trying to make about whether it's this or this, if you go back to your definition of the magnetic force, QV cross B. And if we write out what cross product gives us, it would be QVB sine theta. So it's this part that's kind of, what's in question here. So this is kind of, I'm going to draw it like this, the z plane and the x plane. It's a little bit different than the picture, but we have the B field in the positive z direction and the velocity, not quite that much, but like that with a 30-degree angle between them. And so when we see this VB sine theta, the sine theta is actually associated with the velocity term. So V sine theta, that's a vector component. So based on this picture, which vector component would that be?
The x component.
Yeah, V sub x. So if you make this into a little triangle, and sine is opposite over hypotenuse, then it's this vector component, which if you move it down here, would be V sub x. So what that tells us is that as far as whether it's like this or tilted, our middle finger is always going to be in the direction of B. But our index finger is only going to be in the direction of the x component of V. So though it's not relevant to the answer we're looking for here, you can generalize this to other problems, but your hand would be not tilted, basically. So your finger would be along the x-axis and along the z-axis and along the y-axis. Does that make sense? Okay. Let's double check that the book agrees that the answer is D. Yes, it is. Okay, next one. A charged particle moves through a region of space that has both a uniform electric field and a uniform magnetic field. In order for the particle to move through this region at a constant velocity, what must be true? Anyone need more time? Yes? Okay. All right, who thinks the answer is A? Who thinks the answer is B? Who thinks the answer is C? And I think that's everybody. Okay, so why is the answer C?
The forces on the particle have to cancel out. So the force is perpendicular to the magnetic field and in line with the electric field, and in order for them to cancel out, that means that the two electric and magnetic fields have to be perpendicular to each other.
Great. Good explanation. Do you guys remember what we called this last week?
So the velocity selector device.
Yeah, that was something that made use of it. But I guess the principle at play here, we called it crossed E and B fields. And yeah, the velocity selector is the one that would, a device that makes use of that. So, all right.
It's not moving, right?
What's that?
The constant velocity is 0.
Nope, the constant velocity is some value that's not changing. So this is, the velocity selector you put in a beam of particles into an electric field and a magnetic field that are perpendicular. And if those fields are tuned correctly, then your beam will come straight down out of the velocity selector. And then we learned that you can also do this for those old tube TVs using a cathode ray tube and tune the B field and the E field so that your particle actually bends as it comes out, so you could direct it to a different point on your screen. So there's certainly moving particles here.
Okay.
And anytime we're dealing with magnetic force, we have to have moving particles, because you don't have a magnetic force unless your particle has velocity. Okay, next question. A circular loop of wire carries a constant current. If the loop is placed in a region of uniform magnetic field, the net force on the loop is in what direction?
What is the plane of the loop relative to the force?
That information is not given to us.
Net magnetic, wait, the net magnetic force.
Who's ready to vote? Okay, we'll take a stab at it and we'll talk about it. Who thinks the answer is A? Nobody. Who thinks the answer is B? Oh, left-hand rule. Banishment.
That was a bad word.
Yes. I yelled at Kelsey. Who thinks the answer is C? Who thinks the answer is D? 1, 2, 3, 4, 5. And who thinks the answer is E? 1. Okay. So 5 people chose D. A lot of people are abstaining, which is fine. Why did people choose D, since there was 5 of you who thought it was D? Anyone want to take a stab at that one?
I'll take a stab at it.
Sure.
So I'm not sure if it matters what direction the magnetic field is actually in, but if the force on this side of the loop goes like in this direction, then the force on this side of the loop has to go in the opposite direction.
So that
So
instance it would.
they will cancel each other out.
Wouldn't that accelerate it? If they're
That would make it turn.
yeah, that'd make it
Right.
turn.
So that's
but
torque.
the net magnetic force is still 0, isn't it?
Correct. Yeah, so that was what we learned last week, that you have a net force of 0, but that doesn't mean your torque is 0. And torque is what causes it to turn. So if we're not sure about every instance, that's why I drew a picture on here. The one Nolan brought up would be where the force is coming out of the board on the bottom and going into the board on the top. So what would the magnetic field direction be if that was the case? Jordan says up.
Down.
Nolan says down. Anyone else want to weigh
I
in?
didn't say anything.
Thomas says, okay. Jordan says, don't let me, no, don't quote me on it. Okay.
It's on video, Jordan, it's for the record.
How do we figure it out? Remember, this is a different right-hand rule. The force is equal to the direction of the current IL cross B. So for the right-hand rule, our index finger is in the direction of what? Current. Our middle finger is always in the direction of B, right? The bird, B. So our thumb is in the direction of the force. So Nolan said in one example that the force is coming out of the board, so my thumb is coming out of the board. And at the bottom, the current is going to the left, and that makes my middle finger, let's see, no, my thumb needs to come out of the board again. So my thumb is going down, or my middle finger is pointing down, and we can double check on the top. The force would be going into the board. My middle finger is still pointing down. So in that instance, the B field would be pointing down. If the B field is pointing up, that would just reverse it. So the force is coming out of the board on top, and let's see, B field up, out of the board on top, and into the board on the bottom. And let's see, if your B field was going into the board, what would the direction of your forces be on the top and the bottom of that loop?
It would just be outward in all directions around the loop.
Oh, okay, so in the plane of the board, but like this.
So they all cancel out.
Okay, do other people agree with Jordan?
That's right.
Let's see, B, yeah? That one's easy because you can just do this with your hand.
So that's the example I was thinking of that maybe think B.
But that wouldn't change, oh, D, yeah, 0, yeah, exactly. So we've given multiple examples, and every time the forces all cancel. Okay. Any other questions or thoughts on this problem? Yeah, Liz?
Can you figure out what the electric field is for this, or is there not? Because it's all inside the wire.
There is no outside electric field in this problem. Inside the wire you would have some kind of electric field, but it would be kind of a negligible thing. It wouldn't really drive any of the behavior. But I would, just because you have charged particles and they're all creating electric fields, then you'd have some kind of electric field. What that would look like.
Like, I guess another question, kind of going off that, has there ever been a motor that uses both the magnetic and the electric field?
There very well could be, but I'm not aware of it. That's a good question for one of the engineering instructors that teaches motors. My knowledge of motors is pretty limited, but I wouldn't imagine that there isn't. I mean, it seems reasonable that there could be. Yeah. Any other questions? Okay. Similar question, but now it's asking about the net magnetic torque on the loop. So a circular loop of wire carries a constant current. If the loop is placed in a region of uniform magnetic field, the net magnetic torque on the loop is what? I remember changing one of these answers a previous term, so I could change it, or I could let it be a discussion point. But I think the way that these answers are given at this point, it is confusing on more than one level.